Okay, let's go through a few examples. So here I claim let t of n is equal to 2n square plus 1, and I want to prove that t of n is equal to order n square. Okay, now so what is it I need to give? I need to give two constants c and n0 such that t of n is less than or equal to c times n square, where n is greater than or equal to this n0, right? So let me write to prove. So TP, so I mean I'll be using TP from henceforth to mean to prove. Okay, so to prove 2n square plus 1 is less than or equal to cn square for a c c greater than or equal to 1, and for all n greater than or equal to n0. Okay, where n0 is also a number greater than or equal to 1. We have to find such numbers c and n0 first. Okay. Now, so let me just take. So I'm going to take the following. I'm going to take n0 to be 1. So I'm going to take c to be 3 and n0 to be 1. Okay. So then, what does it mean? So it means, so I claim the following now. Okay. So 2n square plus 1 is less than or equal to 3n square for all n greater than or equal to n0. Is this true? If this is true, we have proved, right? Our claim is true. Is this true? So to check whether this is true, I have to do n square is greater than or equal to 1, or n is greater than or equal to 1. This is true since right? Since n is greater than or equal to 1, this is true. Right? Yeah. Okay. Okay. So so what we have is that if t of n is of the form 2n square plus 1, t of n is of the form order n square. Now let me go to the next thing. To n square plus n plus 1. I claim then also t of n is equal to order n square. Okay. So I have to again show so what is it I need to prove? I need to prove okay, this is what I need to prove, right? For for a c, I have to find out a c and an n0 such that this is true for all n greater than n0, right? This is what I need to prove. Now what is a c I can take? I am going to take 2 plus 1, so let me just take c to be 4 and n also to be 1, n0 to be 1. Okay, and I'm going to then write this thing as 2n square plus right. This is true. When I will just substitute. So I have to prove this is true for all n greater than or equal to n0. This is what I need to prove. Now this is true. Let me see to show that. To argue that this is true, we know that n plus 1 is less than or equal. So we have to prove this fact, right? Is this a true thing? Right. Okay, so let me, is n, so let me try to argue n plus 1 is less than or equal to, why is this true? Because n square is, n is less than or equal to n square when n is greater than or equal to 1, right? This, and I'm going to write n square plus n square. 1, I have replaced 1 with n square is greater than or equal to 1, so therefore I can do this. Yeah, so this is done. Hence, since this is true, we have this fact to be true. Okay. Yeah. Good. So what we have shown now is that a polynomial like this 2n square plus n plus 1 is of the form order n square. So this could have been any constant. Okay. These constants do not matter. This could have been 10 and this could have been 27 or this could have been 50. You take any of these constants, it's the fact is that t of n is equal to order n square. That's true. Okay. Yeah. Now next question is the following fact. What about this? Let's say what can I say about this? If my t of n is this, what can I say here? So I claim this is equal to order n cube. Why is it true? What is the proof? I'm going to take my c to be so 15, 17 plus 50, 67. So what I'm taking is the constant 5 plus 10, 15 plus 2, 17 plus 50, 67 I'm taking, and n0 to be, this is what my constants are, okay. And now I need to show, because of this fact, and now I need to show that this is less than or equal to 67 times n cube, right? So what I do is the following. I am going to write 5n cube plus 10n square plus 2n plus 50 is less than or equal to 5n cube this is also true, right? I just replaced this n square n cube, this is less than or equal to, so this is true, right? So I could do this. This is true for any n greater than or equal to 1. And therefore, this is less than or equal to 67 n cube. And hence, because of this, therefore, this is fine, right? Okay. Let's look at a few more examples. What about this? What about this? I'm going to write log n. Is this true? Is this true? T of n is equal to log n, T of n is equal to O of n. Okay. So what is it I need to prove? I need to give C. So C equal to 1 and n is equal to 2. n0 is equal to 2. So I'm claiming that for all n, so log is log to the base 2. Okay. For all n greater than or equal to n0, log n is less than or equal to n. This is true, right? And therefore, this claim is also true. Next thing for us to prove is T of n is equal to n log n. And we are going to prove T of n is equal to order n square. Why is this true? So I have to pick two constants, c equal to n and n0 is equal to 2. I just took that, and I have the fact that for all n greater than or equal to n0, this fact I know. So I'm going to just multiply n here and n square. Right? Okay. So this gives me T of n is equal to all of n square. Right. Now what about this? Again, this is also n square. Why? Because I can do, I'm going to take c to be 2. Okay. So this is n plus n square, which is less than or equal to 2n square. Right? I had to prove c of n square less than or equal to c of n square, and that's what I showed. Let's say T of n is equal to n square. I claim. So is this true? T of n is equal to, yeah, this is true, right? Because you could have just taken c to be 1 and n0 to be 1. Because n square is same as n square. Right. But I claim the following also. Is this true? So this is supposedly bigger thing. Can you do this? N square is equal to O of n cube. Can you do this? Yeah, you can. Because why? Because n square is less than or equal to 1 into n cube for all n greater than or equal to. This is true, right? This c1 is my constant c, and this one is my n0. So any number bigger than, so any function which is bigger than n square, strictly big, bigger for all integers, all numbers is so you can always write n square is equal to big O of n raised to 4 or n raised to 5 or anything like that. Okay, that's the point I was trying to make. So this is, so therefore you can have so n cube is, for example. Okay, so all these things are possible. Now, what is there? Here is another simple case. Okay, T of n is equal to a constant 100. What can I write about T of n? Then this is O of, so this is O of a constant, right? So this is O of 1. Why O of 1? Because now I can write right. This is my constant c, and this is true for all n, right? Because there is no n here itself. Okay, because n is not part of this equation at all, so you can take any n without affecting this, right? So, so this is my c, 100 is my c, and therefore you take any constant here, it is all of the form of n. So this is one reason why when we are looking at linked list, I wrote 1 for even when you had to go to 2 elements. For example, I had written 1 in that place, because I would, in my mind, it's order 1. Okay. So in some sense, if it is a constant, it's saying it is independent of the input size. If you are some algorithm works in O of 1 time, it means it is independent of the input size. It might be just looking at the first digit or something like that and turning and deciding on the output. Next question to consider is T of n is equal to 2 raised to n plus 2, and I have to prove T of n is equal to order 2 raised to n. And here is what I am going to do. what should be the constants, and let me just, I'm going to take C is equal to 4 and N0 is equal to 1. And therefore, I have the following fact. T of n is equal to 2 raised to n plus 2. I know is less than or equal to 2 raised to 2 square into 2 raised to n, or less than or equal to 4 times 2 raised to n, right? That is. It's exactly what we wanted. So T of n is equal to less than or equal to C times 2 of n, where C is equal to 4. This is true for all n greater than or equal to 1. Now, next thing we can consider this. Okay, let's do something different. Let's try to show that. Okay, T of n is equal to 3 of n, and I have to prove that T of n is not equal to order big of 2 raised to n. Okay, so this is 3 raised to n, and this is not order 2 raised to n. This is what I am interested in proving. Okay, so this is what I am interested in proving, and the claim is how do I prove this? So I'm going to assume that there is a constant, and then I show that yeah, it's a contradiction. It's not possible. So let C and then 0 be greater than or equal to 1, such that this is possible. Okay, such that for all we have right. So we are going to assume this. Now, what does this imply? This implies that C is greater than or equal to 3 by 2 raised to n. Okay, so what is 3 by 2? This is some 1.5 raised to n. Right? And can there be a constant like this? So what we have here is that C has to be greater than or equal to 1.5 raised to n for all n. And this is not possible because C is a constant, and I can make n a very big number such that n big 1.5 raised to n gets bigger than C. Okay, because this is an increasing function and this is a constant, right? And it's a constant. So if you draw the graph, C is something like this, and this is an increasing function. And where does it increase? So when n is equal to 1, this will be something like here, right? 1.5. Okay, when n is equal to 0, this will be here 1. Right? So it's growing like this. Right? So there will be a point after which C will be less than 1.5 raised to n. So it's not possible to find such a constant. That's the main point I'm trying to make, and hence this is not possible. Okay. I'm going to have a graph here, and just let T of n be, okay, maybe something else. Let's say this is my function f of n, and I have a g of n like this, let's say. Okay, but some c times g of n will be c times g of n. So this is going to be, so this becomes c times, right? So this is, so here is my f of n function and here is my g of n function. and here is my c times g of n function. So in this case, I can write f of n is equal to big O of g of n. So, okay, is it clear what I'm trying to say? All I'm interested, so g of n can be completely below the function f of n, but c times but the question is always whether there exists some constant such that if I multiply it with a constant, it takes you above. And now I'm supposed that this is going to be always greater than this f of n. Okay, and this is going to be my n0. This is my n0 and this is my constant c, which helps me to prove this stuff. Okay, so this brings us to an end on big O notation. I mean, it's not an end because we are going to see a lot of, big O notation is part of algorithm analysis, and you're going to see a lot of it